Well, it's in healthcare, it's in education, it's in criminal justice, it's in the experience of shopping as you walk down the street. It has pervaded so many elements of everyday life, and in a way that in many cases is completely opaque to people. While we can see a phone and look at it and we know that there's some AI technology behind it, many of us don't know that when we go for a job interview and we sit down and we have a conversation that we're being filmed and that our micro expressions are being analysed by hiring companies, or that if you're in the criminal justice system, that there are risk assessment algorithms that are deciding your risk number, which could determine whether or not you receive bail or not. These are systems which in many cases are hidden in the back end of our sort of social institutions. And so one of the big challenges we have is how do we make that more apparent? How do we make it transparent? And how do we make it accountable?
What are the types of transparency? Well, I put together 3 of them that I think come into play when we look to specifically at machine learning models. First, there's data transparency, and this seems quite obvious. Certainly, it points to the data that I provided to a website or to a data controller like a bank officer. But it turns out that the data that you knowingly and willingly hand over, say your name, address, the date of birth, credit card numbers, and the like, this is just the tip of the iceberg as far as the amount of data that's directly related to you. There's also observed data that systems capture about you and that is most often regarded as the property of the system, not you. Things like how long did you linger on that web page? Notes that you draft, but then later decide not to post or send. Your likes, your Facebook likes. These system observations can be sizable. LinkedIn, for example, claimed that it had over 100,000 variables held on every user that go into machine learning models. Facebook, of course, is notorious for its collected and acquired data, stemming not only from users' interactions with its website or apps, but also from other websites sharing data with Facebook, and then there's data combed from other sources. Well, those data are about you personally. They are not your personal data. They don't belong to you. And then there's bastard data, a great term from Joel McNamee. Basically, bastard data are the offspring from extractions and manipulations of other data, often done using machine learning to create profiling that can then be attached to individuals. McNamee asks, can it really be simply a privacy issue when an individual would not be able to guess that a data exists? Can an individual be in control of data whose nature and existence is unknown and often unknowable? How much more should companies be able to know or guess about you than you know about yourself? Sometimes data may be for a purpose that seems quite disconnected or irrelevant to a decision, such as whether to grant you a loan. Data might be linked to you based on profiling so that, say, your political preferences might be guessed by your music listening preferences. And sometimes a bit of data may act as a proxy for other attributes, which can bias decisions made on those data.
Here is our application, and the customer can choose how many money they want to borrow and how long they want to borrow, and they can input their data here, and after that, you can just borrow very quickly.
The CEO shows us how quickly you can get a loan.
It has done.
It takes an average of 8 seconds.
It has passed 2 banks. Wow. Yeah, our job is finished.
In the 8 seconds, the algorithm has assessed 5,000 personal features from all your data.
12,000 features. That is related with the delinquency. When maybe the banks only use few, maybe 10 features when they are doing their risk management.
Processing millions of transactions, It'll dig up features that would never be apparent to a human loan officer, like how confidently you type your loan application, or, surprisingly, if you keep your cell phone battery charged.
It's very interesting. The battery of the phone is related with their delinquency rate. Someone who has much more lower battery, they get much more dangerous than others.
Then there's algorithmic transparency. It's one thing to have thousands or hundreds of thousands of variables in just a monstrous, mega multidimensional data set. But it's another thing entirely to analyze that data with tools that accept inputs, produce output, but otherwise are inexplicably opaque. That opaque quality of many machine learning approaches is what earns them the name black boxes in popular media. But clarity or explanation is still possible. Some machine learning approaches use decision trees, and they are easily decomposable. That is, they can be taken apart and explained by their design. Other approaches are less yielding. Random forest models are tougher, but they can be created so that they provide variable importance scores that serve to explain points in the model. Very complex deep learning systems are even more difficult. The point is that explaining how a machine learning model works, the mechanism of a decision-making algorithm at its core, can be frustratingly complex and even practically unattainable. Why is that important? We tend to believe that if we are able to see something, to understand it, we can also control it. At least we can understand its capabilities and limitations. If a machine learning model is sufficiently explained, we can understand why, say, a bank loan was denied, even though there may be little we can actually do about the decision. Then there's process transparency. And in a sense, what I call process transparency has to do with the way that data and algorithm are gathered or put together, including how they're versioned and changed, and how machine learning models are then applied to new data. This would also include whether or not you're applying the model in the manner it was designed. In most cases, process transparency allows for the discovery of bungling. Error-ridden data being used to create models, for example. Duct tape, undocumented algorithms. The unfortunate loss of data provenance and therefore confidence in them. These shortcomings undermine models and the data that ground them. And in the case of some applications, a misunderstanding of the purpose of a computer application can work against fairness and clarity in its use. The first two forms of transparency, data and algorithmic, are opaque mainly because of their scale and the complexity. They overwhelm human understanding. The third form, process transparency, while often also complex, includes more easily understood matters of human judgment and decisions. Those decisions, for example, may help show how data is biased or how a decision assist tool would be misapplied. There's another, perhaps more psychological aspect of transparency that I think comes into play. It has to do with our human motivations and our desires surrounding our choices to use models. We do feel we have a certain amount of control when we see what was before opaque. But conversely, and even paradoxically, we also place a lot of trust in automation and computational tools. They seem magical because they're untouched by human whims, biases, and frailties, at least apparently. Sometimes they're pitched to us as more powerful tools than they really are. Surpassing our understanding, they're also thought to be better for that very reason. How do we surmount the challenges that abundant data and complex machine learning systems pose? Overcoming opacity and increasing the clarity are areas of active research in machine learning for obvious reasons. People who use machine learning systems in healthcare, for example, want to have a clear understanding of the mechanisms at work in analysis. And we all want to know that machine assists in the judicial and financial decisions are based on clear and fair rules and processes. A couple of means of explaining machine learning systems have arisen. One focuses on the models themselves in approaches called model-centric explanations. This approach doesn't rely on the data that's put into the model or the decisions that a model produces. It's a way of describing the model quite broadly in an encapsulated form and can include things like the intention behind a modeling process, the kind of model, is it a neural network, a random forest, an ensemble creation? What are the parameters that are used? What is a summary and description of the data that's used to train the model? How well is the model able to predict using unseen data? And can you simplify and give me an incomplete description of how the model takes inputs and arrives at results or outputs? And then, of course, the process information. The idea of a model-centric explanation is to describe the overall engine that moves to a decision. The other approach is called the subject-centered explanation, which focuses on the specific inputs, the specific data that a model accepts, and then processes to a result or an output. With this approach, the behavior of the model is in a sense mapped out by putting in specific inputs and seeing what comes out. For example, would a bank customer with a certain wealth and previous loan payment behavior qualify for a loan of a certain amount? What about when you change a customer's wealth, behavior, and size of the loan? If you query the model enough times, you begin to see patterns of response that help you explain the characteristics of the model. According to Lillian Edwards and Michael Veal, there are 4 kinds of these explanations. They're sensitivity-based, case-based, demographic-based, and performance-based. Each of these probes a different quality of a model. A demographic-based explanation, for example, finds out what kinds of groups of inputs are created, while a performance-based explanation looks at the accuracy of models and finds their hard cases that come in as the inputs. These are important means for gaining clarity. Hani Farid of Dartmouth University used the subject-centric method to probe COMPAS, an application that courts use to predict recidivism. COMPAS was shown to be significantly biased, and Farid and his students unpacked the reason why.
So in this study, we learned 2 important things, and they go beyond these predictions in the criminal justice system. 1, big data, data analytics, AI, ML are not inherently more accurate, more fair, less biased than humans. Simply hiding behind technology does not make you better. And this is particularly true when the data that is being fed into these algorithms mirrors existing social inequalities. And the danger here is that you hide behind that, right? You forget that you're feeding data into the system that is what is happening in the world around us. These predictive algorithms are meant to overcome the limitations, and they are simply mirroring them. And that is very dangerous. Number 2, it is dangerous and it is reckless to unleash predictive algorithms like this without thoroughly understanding how they work, without thoroughly understanding their accuracy, and without thoroughly understanding their fairness. And that is true in the criminal justice system. It is true for employers and universities making admissions and hiring decisions. It is true in financial institutions making loan and mortgage decisions. Those 3 things are some of the biggest things that we do in our lives: our civil liberties, our financial well-being, and our employment. And we are turning over decisions to computerized algorithms, and that is very worrisome to people like me as technologists.